This video talks about the arc length and the area of a sector of a circle, and also we'll talk about how to calculate the linear and angular velocity. So first up is arc length. So what is the arc length? Now if we have a central angle denoted by theta, so that's central angle here, and then the arc length of an intercepted angle in a circle is this distance right here. Okay, so S denotes the arc length, and then the R is just the radius of the circle. There are two ways to calculate the arc length. One is theta equals S over R. The key point here is that theta must be in radians. So if we're given a central angle that is measured in degrees, we must first convert that angle into radians for us to be able to use this formula. And the second way to calculate the arc length is what I like to call the part and whole method. Okay, so what we do is we take the arc length, which is S, so that's part of the circumference of a circle. Now the entire circumference of a circle can be calculated with the formula for circumference, which is 2 pi r. Okay, so we have part over whole. Okay, so we have the part of the circumference, which is the arc length, S over 2 pi r, and that is going to equal the central angle, which is theta, divided by 360 degrees. So theta is part of the measurement of that angle inside of the circle, and then 360 degrees is the entire measurement of that central angle in a circle. So let's look at this example, and we'll solve this example both ways. So it says a circle has a radius of 18 inches. Find the length of the intercepted arc if the central angle is 210 degrees. So looking at a diagram of what's happening here, we have a central angle that's 210 degrees. So this distance right here, we'll call that theta. So theta is equal to 210 degrees. And we have a radius that is measuring 18 inches. So we'll have R here. So that radius is 18 inches. So if we wanted to solve this with the first method, well, that's going to be theta equals S over R. Now remember, theta must be in radians, so we need to convert that angle measure, which is 210 degrees, we need to convert that into radians. So to do that, we multiply by pi over 180 degrees. The degrees cancel. We end up with 210 pi over 180, the zeros cancel, 21 over 18, divide both of those by 3, we get 7 pi over 6. So that's the radian measure of that central angle. Okay, so in the formula right here, we're going to say 7 pi over 6 equals S, which is the arc length, divided by the radius, which is 18 inches. And the arc length that we're looking for, I didn't label it here, but it's going to be that distance right here. Actually, we want the angle, we want this distance where that central angle is opening up. So that's the arc length right there. So all we need to do is cross multiply to solve for S. So multiply both sides by 18 inches. That cancels over here. We're going to do times 18. So 18 divided over 6, I can reduce that, so that's going to be 3 over 1. So 3 times 7 pi is 21 pi over 1, and that's going to be in inches there. Alright, so that's the first method for finding the arc length, just using the formula. The second method is what I again call the part and whole method. So we're going to take part of the circumference, which is the arc length, divided by the entire circumference. Well, that's 2 pi r. And we set that equal to the central angle, which is part of the angle of the circle. that's going to be theta, divided by the entire angle of the circle. We'll call that 360 degrees. So we're trying to solve for s, which is the arc length. So we're going to say s over 2 times pi times the radius, which is 18, equals the central angle. Now when we use this method, we do not need to convert the degrees into radians. So 210 degrees over 360 degrees. Well, I can simplify this fraction over here on the right. I can cancel out the zeros. 21 over 36, well, what is that? I can divide both of those by 3. I get 7 over 12. Then on the left-hand side, we get s over 2 times 18 is 36, so let's write that as 36 pi. So we're trying to solve for s, so I'm going to multiply both sides by 36 pi. Okay, so we end up with s is equal to, well, 36 over 12 is 3 over 1. So I'm going to do 7 times 3 is 21. And don't forget about the pi. So we end up with 21 pi, and that's in inches. So either way that we do this, we end up with the exact same value for the arc length. Now the benefits of using method 1 versus method 2, well, in method 1 we need to do this step right here where we must convert from degrees to radians. If we use the part and whole method, there's no conversion that needs to take place, and frankly this is a little bit more intuitive on how we solve this. This formula may not be as easy to remember as just remembering, well, we always just do the part that we're looking at divided by the whole that we're looking at, and we set that equal to each other. Moving on, we will discuss the area of a sector of a circle. Now what we mean by a sector is when we have a central angle, the sector is the area right here. Okay, so this is still defined by the radius of the circle and the central angle, and we're calling that central angle theta. And so there's two ways to find the area of a sector, much like finding the arc length. We have a formula that we can use. I'm denoting the area of a sector as AS. So AS is equal to r squared theta divided by 2. And again, just like the arc length, theta must be in radians. Students miss this question if the main reason students miss this question, they use the formula correctly, but they do not convert theta into radians. So make sure that you do this. Must be in radians. Second way, again, we can use the part and whole method. So we're going to say part over whole. Well, what we're talking about is the area of the sector is a partial area of the entire circle. So the area of that sector is what we're looking for, divided by the entire area of a circle. Well, the entire area of a circle is pi r squared. Okay, and we set that equal to the central angle, which is partially around the circle. So we're going to say theta divided by 360 degrees. And let's attempt an example that deals with the area of a sector. We have a question that says, how many square inches of pizza have you eaten if you ate a sector of an 18-inch diameter pizza whose edges form a central angle of 30 degrees? So what does this mean? Well, we have a pizza. The radius, actually it says the diameter is 18 inches. So that's D. We're going to say D is equal to 18 inches. And then we have a central angle of 30 degrees. So central angle, let's call that theta, and we'll say that theta is equal to 30 degrees. And we're going to solve these questions, or this question, using both methods again. So with the first method, we use the formula. So the area of the sector is equal to r squared theta divided by 2. So we have the radius. Well, the radius is equal to the diameter divided by 2. Well, the diameter is 18 divided by 2, so the radius is 9 inches. So be careful here when this question talks about the diameter. That's actually not the radius. So we need to know how the diameter and the radius relate to one another. Next up, we have an angle that's 30 degrees, but we must convert that into radians. So doing so, we take 30 degrees, we multiply by the conversion factor pi over 180. Well, we end up with 3 pi over 18, which divide both of those by 3, we get pi over 6. So we have theta, so now we can plug everything into the formula up here. So we're going to say the area of the sector is equal to the radius, which is 9, so 9 squared times theta, which is pi over 6, divide that by 2. Then we just need to do some simplification. 9 squared is 81 times pi over 6 all over 2. And to simplify this, we could say 81 pi divided by 12. And what can we do? We can divide the top and bottom by 3. So 81 divided by 3 is 27. So 27 pi. 12 divided by 3 is 4. So we're going to say 27 pi over 4. And our unit here is going to be inches squared because way back here we did 9 squared, and that was 9 inches. So the inches is getting squared. So our unit here is inches squared. All right, and then the second method here is we'll use the part and whole method. Okay, so part of the area of the circle is that sector. So we're going to say the area of the sector over the entire area of the circle, which is pi r squared. That's equal to the central angle divided by 360 degrees. So we're trying to find the area of the sector divided by pi r squared. So pi times 9 squared is equal to the central angle, which is 30 degrees, divided by 360 degrees. Well, I can simplify this fraction on the right-hand side, divide both by 10, and then I can divide 3 over 36, both of those by 3, we get 1 over 12. And then on the left-hand side, we're going to say the area of the sector is equal to 81 pi, so that equals 1 over 12. So multiply both sides by 81 pi times 81 pi. We get the area of the sector is equal to 81 pi over 12. And again, that's just what we had over here. So I can divide the top and bottom by 3. We get 27 pi over 4 inches squared. So again, we get the exact same answer no matter which way we go about solving this question. And personally, I think this second method is easier and more intuitive. And we are going to finish up this video by discussing linear and angular speed, or linear and angular velocity. So we'll do this through an example. The example says, suppose a runner runs in a circle 100 feet in 5 seconds. What is the linear speed of the runner in feet per second? So the question is asking us to find the linear speed, and it's asking us to measure this in feet per second. Now, in general, anytime we are talking about linear speed, we always discuss this in the change in distance over the change in time. Okay, and you're familiar with this when you're driving your car. If you're driving on a straight road and you go 60 miles in 1 hour, well, the change in distance was 60 miles. So 60 miles traveled in a time of 1 hour. That's an example of a linear speed. So for this question, it says, suppose a runner runs on a circle of 100 feet in 5 seconds. Well, the distance traveled is 100 feet, so we'd say 100 feet over 5 seconds. So the distance over the unit time is 100 over 5, or 20. So we'd say 20 feet per second would be the linear speed. Now, I think most of us are pretty familiar with linear speed. Angular speed is a little less familiar to us. Now, angular speed, what this is talking about, angular speed is defined as the change in an angle, so delta angle, divided by the change in time. So what do we have here with this question? Well, what it's saying is we have a circle. The circle has a radius of 40 feet, and we want to know what's the angle that this runner passes through after 5 seconds. So let's suppose after 5 seconds the runner has traveled this distance. So what's happening is this angle is opening up after 5 seconds, and we want to know how quickly is that angle changing. So to do this, we're going to say angle, well, theta, we know that that's s over r here. That's just coming from the formula for the arc length. Well, we need to know what that central angle is. So that central angle, well, the arc length, the distance traveled, let's see here. This question is a callback to the previous question where it says the runner is on a circle, travels 100 feet. So this distance, this arc length is 100 feet. So we have 100 feet divided by the radius of 40 feet. So theta is going to be 100 over 40. If we divide that, we get 2.5 radians here. So to find this angular speed, what we do is we take the change in that angle. Well, the angle has changed by 2.5 radians in a time of 5 seconds. So if we reduce this, well, 2.5 out of 5, that's 1/2, or 0.5. So we'd say the angular speed is 0.5 radians per second. Now we want to be able to convert between linear and angular velocity. So we do that, we say the radius times the angular velocity is equal to the linear velocity. So if we know 2 of these things, we can get the third. So typically we'll be given a linear velocity, so something is traveling on a circle, and in that circle we'll know what the radius is, so we can solve for the angular velocity. And then lastly, this example says a model plane is attached to a swivel so that it flies in a circular path at the end of a 12-foot wire at the rate of 15 revolutions per minute. Find the angular speed and the linear speed of the plane. Now what this is saying is we have a plane, and every minute it travels around this circle 15 times. So 15 revolutions per minute here. All right, and we also know that the radius is 12 feet. All right, so we need to find the angular velocity and the linear velocity. Now, it doesn't really matter which one we do first here. I actually think I'm going to do the linear velocity first. So the linear velocity, remember, is the change in distance over time. Well, we don't really have a distance here. We just have this 15 revolutions per minute. So that's revolutions over unit time. We want the distance over unit time. So what we do is we need to convert that 15 revolutions per minute into some unit of distance divided by time. And we already have a unit of time here with this minute. So we need to convert the revolutions per minute into distance per minute. Now what we have, or what we're going to do, is we're going to multiply by a conversion factor. So for this conversion factor, we want to know what's the distance traveled in 1 revolution. Well, the distance around the circle, that's also called the circumference, and the circumference is 2 times pi times r. So the circumference here is going to be 2 times pi times whatever the radius is, which is 12 feet. So the circumference is 24 pi feet. So the distance traveled in 1 revolution is 24 pi over 1 revolution. And we're going to write this as feet. So the revolutions will cancel. We have 15 times 24 pi. That comes out to 360 pi feet. for a single minute, and that, if we calculate that with the calculator, it's about 100 or 1,131 feet per minute. So that would be the linear velocity here. Now let's discuss calculating the angular velocity, and we'll do this in two ways. So the angular velocity, remember, is the change in the central angle divided by the time here. So again, we have this ratio, 15 revolutions per 1 minute, and what we want to do is we want to get this into some angle measurement. So we're going to turn this into radians. So how many radians does this plane go through in a single revolution? Well, once around the circle, we saw that that is 2 pi radians. So that's going to be the conversion factor. So the revolution will cancel. So 15 times 2 pi, that's 30 pi radians for a single minute. And punching this into the calculator, 30 pi, we get about 94 radians per minute. So a second way we could have gotten that angular velocity is if we use this conversion from before that we talked about, this down here. So radius times the angular speed is equal to the linear speed. Well, if we already had the linear speed, that was 1,131. That is equal to the radius, which is 12 feet, times the angular speed. So if we just divide both sides by 12 here, kind of running out of room, but that's going to get us about 94 radians per minute, and that's exactly what we had here. So if we find either the linear velocity first or the angular velocity first, we can then just go down here, use this conversion, and we will be able to convert from one unit of speed to the other.